Hey there, welcome back. Hope you're doing awesome. Tonight, we're jumping into one of the most basic ideas in science, and honestly, one of the most fundamental things in the entire universe: energy. What is energy, really? We use the word all the time, but do we actually know what it is? What are the different kinds, like light energy, heat energy, chemical energy, and all the rest? And what is energy even made of? If that sounds interesting, you're in the right place. Get ready to dive into the amazing world of science. And hey, if you're into topics like this, make sure you hit that subscribe button and turn on notifications so you don't miss out. All right, let's get into it. Picture a child on a swing at sunset. The swing moves forward, then back, forward, then back. The child's hair flows with each movement. Their laughter fills the air. Something is happening here, something you can see and feel, but what is it exactly? What makes the swing move? What makes the child laugh? What makes the sun slowly sink toward the horizon as this beautiful moment unfolds? Think about everything you've ever witnessed. A lightning bolt splitting the sky. A waterfall crashing down a cliff. Your own heart beating in your chest right now. A campfire crackling on a cold night. A flower slowly opening its petals to greet the morning sun. All of these moments, every single one of them, involves something. Something invisible. Something that flows and changes and moves through everything. This something has a name. We call it energy. And here's the remarkable truth. Everything you've ever seen, everything you've ever felt, everything you've ever experienced in your entire life involves this one mysterious thing. Every thought you've had, every step you've taken, every breath, every blink, every moment of your existence has been energy at work. So we arrive at a simple question. What exactly is energy? If it's everywhere, if it's in everything, if it's responsible for literally every event that has ever happened in the history of the universe, then what is it? Where does it come from? Where does it go? Can it be created? Can it be destroyed? And most importantly, why should you care? In the next 2.5 hours, we're going to answer these questions together. We're going to uncover one of the deepest mysteries of existence. Not with complicated mathematics or confusing jargon, but with simple observations and clear thinking. By the end of our journey, you'll see the world completely differently. You'll understand what you really are. And you'll know the answer to a question that puzzled humanity for thousands of years. Let's start with something you know intimately, something you felt thousands of times. Imagine waking up in the morning after a terrible night's sleep. You stayed up too late. You tossed and turned. And now your alarm is ringing. You drag yourself out of bed. Your limbs feel heavy. Your thoughts move slowly. Everything is difficult. You feel, in a word, drained. Now imagine a different morning. You went to bed early. You slept deeply and peacefully. You wake up naturally without an alarm. Your eyes open and you feel ready. Your body wants to move. Your mind is clear. You feel, in a word, energized. What's the difference between these two mornings? Something is high in the second scenario and low in the first. You can't see it, you can't touch it, but you can absolutely feel it. Your body is trying to tell you something important. It's saying, I need something to function. And right now, I don't have enough of it. Let's stay with this feeling a little longer. Imagine you haven't eaten all day. It's late afternoon now. Your stomach growls. You feel weak. You might even feel irritable or foggy. Your body is sending you an urgent message. It's running low on something critical, something it needs to keep going. So you eat. Maybe it's a sandwich, or a bowl of rice, or a piece of fruit. You chew. You swallow. And then, slowly, something changes. Within minutes, that desperate feeling begins to fade. Within an hour, you feel completely different. You can think clearly again. You can move normally again. You feel like yourself again. But here's the profound mystery hidden in this everyday experience. What just happened? You put food into your mouth. Somehow, mysteriously, that food became the ability to walk, to run, to think, to laugh. The sandwich became movement. The rice became thoughts. The fruit became warmth in your body. How? What's the connection between eating and being able to do things? This is your first real encounter with energy. Not the word, but the reality. Humans have always felt this. For hundreds of thousands of years, long before we had any scientific understanding, we knew something moved through us. We knew we needed food to keep that something flowing. We knew rest restored it. We knew cold took it away and warmth brought it back. We felt energy in our bones, even though we couldn't explain it. And this feeling, this intuition that something invisible makes things happen, this is where our story truly begins. Let's travel back in time, way back. 100,000 years ago, the world is darker than you can imagine. There are no cities, no streetlights, no houses with warm glowing windows. When the sun sets, darkness falls completely. Picture a small group of early humans huddled together in a cave. Outside, the night is cold and full of sounds, sounds that mean danger. The humans are frightened, they're cold, they're vulnerable. This is what every night was like for them. Then, suddenly, something incredible happens. Lightning strikes a tree just outside the cave. The tree catches fire, and in an instant, everything changes. There's light, there's warmth. The frightening sounds from the darkness grow distant. The humans cautiously approach the burning tree. They've never felt anything like this. Warmth seems to flow out of the fire like water flowing from a spring. Light pushes back the darkness. For the first time, they feel safe at night. But then, slowly, the fire gets smaller. The warmth fades. The light dims, and eventually the fire dies completely. The tree is now just black, crumbling ash. The warmth is gone. The light is gone. Everything has returned to cold and darkness. Where did the warmth go? It was there, pouring out of the fire, and now it's nowhere. Did it go into the air? Did it disappear into nothing? And more mysteriously, where did it come from in the first place? The tree was just sitting there, solid and still. Then lightning touched it, and suddenly enormous amounts of warmth and light came flowing out. How was all that warmth hiding inside a tree? Now imagine the breakthrough moment. Imagine the first time a human learned to make fire themselves. Maybe they rubbed sticks together, or struck stones, or used a bow drill. However it happened, they made warmth appear out of nothing. Just by rubbing and friction and effort, they could create what lightning creates. They could make cold wood burst into flames. This must have felt like magic, like a superpower, and in a way it was, because they had learned to release something hidden, something stored, something that was always there in the wood, invisible and waiting. They noticed patterns. Fire needs wood or grass or something to burn. You can't make fire out of rocks or water. Wind makes fire stronger, but too much wind blows it out. Water kills fire instantly. Fire always makes smoke. Fire always rises upward. Hot air goes up, cold air sinks down. These observations were the beginning of science, even though they didn't call it that. But the central mystery remained unsolved. What is fire really releasing? Where does the warmth exist before the fire? And where does it go when the fire dies? As humans became more observant, they noticed invisible powers everywhere. The sun was the most obvious one. Every morning it appeared and brought warmth. Every evening it disappeared and the world grew cold. The sun could warm your skin from millions of miles away. How? What was traveling between the sun and your face? Rivers puzzled them too. Water always flows downhill, never up. It pushes stones. It carves through rock over time. A river can move a massive boulder that 100 men couldn't budge. Where does the river get its pushing power? Why doesn't it run out? Wind fills sails and pushes ships across oceans. Wind tears down trees. Wind brings storms. Yet wind is invisible. You can only see what it does, never the wind itself. It's pure, invisible power, moving through the world. Animals move on their own without being pushed. A deer can run, stop, change direction. A bird can fly. A fish can swim. They seem to have power inside them, power that lets them move themselves. Where does that internal pushing force come from? Why do animals need to eat, just like humans do? Plants seem to grow by magic. You put a tiny seed in the ground. You give it nothing but water and sunlight. Months later, there's a tree taller than a house. Where did all that wood come from? How did something so small become something so large? What invisible process was building the tree? Thunder shakes the ground. Earthquakes split the earth. Tides rise and fall with the moon. Everywhere they looked, ancient people saw enormous powers at work, powers they couldn't touch or see directly, powers they could only witness through their effects. For most of human history, these were simply mysteries. Some people called them the work of gods. Others just accepted them as the way the world is. But a few people, a few curious souls, started asking why. They started trying to understand the invisible forces that make everything happen. And when they did, when they started following that curiosity wherever it led, they began to unlock the deepest secrets of reality itself. Fast forward to the 1600s. Science is just beginning to take shape. People are starting to measure things carefully, to do experiments, to look for patterns in nature. and one of the biggest puzzles they're trying to solve is heat. Everyone can feel that heat moves. Put your warm hand on a cold metal spoon, and the spoon gets warmer while your hand gets cooler. Put ice in warm water, and the ice melts while the water gets colder. Heat always flows from hot things toward cold things. Always. No exceptions. But why? And what is heat, really? Some scientists developed a theory. They thought maybe heat is an invisible fluid. They called it caloric. According to this idea, hot objects are full of caloric fluid, and this fluid flows into cold objects just like water flows downhill. It seemed to make sense. It explained why hot things cool down. The caloric fluid was leaking out. But there was a problem with this theory. A big problem. And a man named Count Rumford discovered it by accident. Rumford was supervising the boring of cannons. You see, cannons are made by drilling a hole through a solid piece of metal. This drilling creates friction, and friction creates heat. A lot of heat. The metal gets so hot you can barely touch it. Now, according to the caloric theory, the heat should be coming from inside the metal. The drilling is squeezing caloric fluid out like wringing water from a sponge. But Rumford noticed something strange. The drilling could go on and on and on. The heat never stopped coming. You could drill the same piece of metal for hours, and it would keep getting hot again and again. If heat was a fluid inside the metal, it should eventually run out. You should be able to squeeze all the caloric out, and then the metal would stay cold. But that never happened. The heat was endless. As long as you kept rubbing and drilling, heat kept appearing from nowhere. Rumford realized something profound. Heat isn't a substance inside objects. Heat is something that's happening. The rubbing, the friction, the motion of drilling, that's what creates heat. Motion becomes heat. They're connected somehow. They're different forms of the same thing. Around this time, scientists started using a new word more carefully. The word was energy. It came from ancient Greek, from the word energeia, which meant activity or operation. Energy wasn't a thing. It was the ability to do things, to make things happen, to cause activity. This was the beginning of a revolution in understanding. Heat wasn't a substance flowing between objects. Motion wasn't just movement. They were different faces of something deeper. Something that could change from one form to another, but was always the same thing underneath. But they needed proof. They needed careful measurements. They needed someone to show exactly how motion becomes heat, and that someone was brewing beer in England. In the 1840s, in Manchester, England, there lived a young man named James Prescott Joule. He was the son of a wealthy brewer, and he had the time and money to pursue his curiosity. And Joule was curious about something specific. He wanted to know the exact relationship between motion and heat. The question seemed simple enough. If rubbing creates heat, then how much rubbing creates how much heat? Is there a precise exchange rate? Can you measure it? Joule set up an experiment that was brilliant in its simplicity. He took a container of water. In the water, he put a device with paddles that could spin around. He attached these paddles to weights on strings. When the weights fell, they turned the paddles. The paddles stirred the water, and the stirring created friction in the water. Then Joule did what made him special. He measured everything with extraordinary care. He weighed the falling weights. He measured how far they fell. He measured the temperature of the water before and after. He repeated the experiment again and again, always checking his measurements, always making sure he wasn't making mistakes. And what he discovered changed everything. The falling weights made the water warmer, every single time. And it wasn't random, it was precise. A specific amount of falling motion always created a specific amount of warmth. The exchange rate was always the same. If you dropped weights from twice as high, the water got exactly twice as warm. The relationship was perfect and unchanging. What Joule had proven was extraordinary. Motion and heat aren't just similar things. They're the exact same thing in different forms. The energy of the falling weights transformed into the energy of heat in the water. Nothing was lost. Nothing was created. The energy just changed its appearance. Imagine transforming $1 into euros. You don't have dollars anymore, but you haven't lost any money. You just have the same value in a different form. That's what was happening with motion and heat. Same energy, different form. Joule published his findings. At first, many scientists were skeptical. The numbers seemed too neat, too perfect. But Joule had been so careful, had repeated his experiments so many times, that eventually people had to accept it. Motion is heat. Heat is motion. They're interchangeable. This was revolutionary. Because if motion and heat are the same thing, what else might be the same thing? What else might be energy in different disguises? The middle of the 1800s was an extraordinary time for science. Multiple people, working independently in different countries, were all arriving at the same profound realization. Something was conserved in nature, something that never increased and never decreased, but only transformed from one type to another. In Germany, a young man named Hermann von Helmholtz was working on this problem. Helmholtz was trained as a doctor, but his passion was physics. He was trying to understand living things, trying to figure out what made organisms different from machines. And he kept coming back to this idea of conservation. He realized that all the various phenomena in nature, all the pushing and pulling and heating and moving, they all seemed to be connected. You could trace them back to each other. The falling water in a waterfall could turn a wheel. The turning wheel could grind grain. The ground grain could be eaten. The food could make muscles move. The moving muscles could lift water back to the top of the fall. It was a circle, an endless cycle of transformation. Helmholtz wrote a paper that shook the scientific world. He called it On the Conservation of Force, though we would call it energy today. His claim was bold and absolute. Energy cannot be created from nothing. Energy cannot be destroyed into nothing. Energy is eternal. The total amount in the universe is fixed forever. It only changes form. This wasn't just Helmholtz. Scientists across Europe were reaching the same conclusion around the same time. It was as if the idea's time had come. Julius Robert Meyer in Germany, William Thomson in England, Rudolf Clausius in Prussia, they were all discovering pieces of the same truth. energy is conserved. Think about how radical this claim is. The universe contains a fixed amount of something. This something has been here since the beginning. It will be here at the end. It can never increase. It can never decrease. Every event that happens is just this something rearranging itself, changing its form, moving from place to place. But the total? The total never changes. This is the law of conservation of energy. It's one of the most important discoveries in all of science, maybe the most important, because it means the universe keeps perfect books. Every bit of energy is accounted for. Nothing appears from nowhere. Nothing disappears into nowhere. You might be thinking, okay, that's interesting, but what actually is this energy thing that's being conserved? We know it can be motion, we know it can be heat, but what is it really? What's the substance? What's the stuff? And here's where things get really interesting, because energy isn't a stuff at all. It's not a substance. It's not made of anything. Energy is a property, a measurement, an idea. It's the ability to make things happen. It's the capacity to cause change. It's what you measure when you ask, how much making things happen power does this object have? So we're chasing something invisible that isn't even a thing. We're tracking an ability, a potential, a capacity. And yet this invisible, intangible idea is the most fundamental aspect of reality. Everything that happens is energy-changing form. Everything. But I'm getting ahead of myself. We need to understand the different forms energy can take. We need to meet energy's many disguises. Because until you know all the ways energy can appear, you can't fully appreciate how strange and wonderful it really is. Let's start with the simplest, most obvious form of energy, the kind you can see with your own eyes. Motion. Picture a ball rolling across the floor. Not fast, just a steady roll. That ball has energy. We call it kinetic energy. Kinetic comes from a Greek word meaning motion. Kinetic energy is the energy of movement. It's energy you can see. Here's what's beautiful about kinetic energy. You can calculate exactly how much a moving object has. It depends on two things, how heavy the object is and how fast it's moving. Makes sense, right? A heavy thing moving slowly has energy. A light thing moving quickly has energy. A heavy thing moving quickly has a lot of energy. But here's something surprising. Speed matters much more than weight. In fact, speed matters so much that if you double the speed of something, you don't double its energy. You quadruple it, 4 times as much. Triple the speed and you get 9 times the energy. This relationship is powerful and important. Let's see what this means in practice. A bee buzzing through the air has kinetic energy. Not much because the bee is light and not moving terribly fast, but it has some. That tiny amount of energy lets the bee fly, lets it move through space, lets it be where it wasn't a moment before. Now think about a car driving down the highway. The car is heavy, much heavier than a bee, and it's moving fast, maybe 60 miles per hour. That car has enormous kinetic energy, thousands and thousands of times more than the bee. You know this intuitively. If a bee bumps into you, nothing happens. If a car bumps into you, even slowly, it's dangerous. That's energy at work. Scale up even more. Think about a jumbo jet taking off. Hundreds of tons of metal and fuel and people moving hundreds of miles per hour. The kinetic energy is staggering, almost unimaginable. That's why planes can fly across continents. They have enough motion energy to push through the air for hours and hours. Now let's go to the extreme. Picture a meteor entering Earth's atmosphere. It's heavy, yes, but the speed is what matters. Meteors move at tens of thousands of miles per hour. Remember, when you increase speed, energy increases by the square. So a meteor moving 10 times faster than a car has 100 times the energy per pound. Moving 100 times faster? 10,000 times the energy. This is why meteors create massive explosions when they hit. They're not bombs, they're not carrying explosives, they're just rocks. But they're rocks with so much kinetic energy that when they suddenly stop, all that energy has to go somewhere. It becomes heat, light, sound, and destruction. Pure motion energy, released in an instant. Here's a sobering thought. A small object moving incredibly fast carries more energy than a large object moving slowly. A grain of sand moving at nearly the speed of light would carry more energy than a mountain. This is why space debris is so dangerous. A paint fleck in orbit moving at 17,000 miles per hour can damage a spacecraft. It's tiny, but it's moving so fast that its kinetic energy is devastating. So, kinetic energy is real, it's measurable. You can see it and feel it. But where does it come from? When that ball starts rolling, where did its motion energy originate? And when the ball stops, where does the energy go? To answer that, we need to talk about energy's greatest magic trick. The energy that hides in plain sight, waiting to become motion. Drop a ball from your hand. Watch it carefully. What happens? It falls, yes. But notice something else. It speeds up. It's moving faster at the bottom than at the top. By the time it hits the ground, it has kinetic energy, motion energy. But at the top, when you were just holding it still, it had no motion at all. So where did the motion energy come from? It appeared during the fall. The question is, was it created from nothing? Or was it already there somehow, hidden? This is where we meet one of energy's most clever disguises. The ball at the top had energy. You just couldn't see it. It had potential energy. Potential meaning it could become kinetic but hasn't yet. It's stored energy, waiting energy, tomorrow's motion energy. Height stores energy. That's the simple truth. Lift something up, and you're storing energy in that height. The higher you lift it, the more energy you store. And gravity will release that energy any time you drop the object. Think about a waterfall. At the top, water sits in a lake or river. It's barely moving, but it's high up. Then it reaches the edge and falls. As it falls, it speeds up. By the time it hits the bottom, the water is moving fast and hitting with force. The height became speed. Potential energy became kinetic energy. This is how old-fashioned water wheels work. The falling water has energy from its height. That energy gets transferred to the wheel, making it turn. Humans have been using height energy for thousands of years, even before they understood what they were doing. A roller coaster is a beautiful demonstration of this transformation. At the start, a motor pulls the cars up to the highest point. That motor is adding energy to the system, storing it in height. Then you reach the top and start falling. The potential energy converts to kinetic energy. You speed up. At the bottom of the first hill, you're moving fast. You have lots of kinetic energy. Then you start climbing the next hill. As you go up, you slow down. Kinetic energy is converting back into potential energy. At the top of the second hill, you've traded speed for height again. Then you fall again, and height becomes speed. The entire ride is energy converting back and forth, potential to kinetic and back again over and over. But notice something important. The second hill is never as high as the first. Why? Some energy is leaking away. Friction with the air, friction with the track, sound as the cars rumble along. That leaked energy becomes heat. So each hill has to be lower than the one before, because there's slightly less total energy available each time. The ride is literally running out of energy. Your own muscles lifting a book are doing something profound. You're taking energy from your body, energy that originally came from your breakfast, and you're storing it in the height of the book. When you set the book on a high shelf, that shelf is now storing energy that came from your food, that came from plants, that came from the sun. You're moving energy through a chain, and height is one of the links. This idea of potential energy is elegant. It means energy can hide. It can wait. A rock sitting on a cliff has potential energy. It might sit there for 1,000,000 years, and that energy just waits. The moment the rock falls, the energy reappears as motion. It was there all along, patient and invisible. And here's a profound realization. Kinetic and potential energy are constantly trading places. A swinging pendulum converts potential to kinetic at the bottom of each swing, then back to potential at the top. A bouncing ball does the same thing. Up and down, potential and kinetic, potential and kinetic. It's like a dance, energy-changing partners, but never leaving the dance floor. Now we've seen two forms of energy, motion and height. But we're just beginning, because there's another form of energy that's hiding right in front of your eyes. It's in everything you can touch. It's in the air around you. It's in your body right now. And understanding it will change how you see matter itself. You're holding a cup of hot coffee. You can feel the warmth. But what is warmth really? What's actually happening when you feel heat? To understand, we need to zoom in, weigh in, past what your eyes can see, past what microscopes could see for most of history. We need to look at matter at the atomic level. Everything solid you've ever touched is made of atoms. Your table, your phone, your own hand. And here's what's extraordinary. Those atoms are not still. They're never still. Every atom in every object is constantly jiggling, vibrating, bouncing around. Always. Even in the coldest ice, even in the hardest steel. Atoms are in constant motion. Temperature is the average jiggling speed. That's it. That's all temperature is. Hot objects have atoms dancing wildly, moving fast, bouncing with energy. Cold objects have atoms barely moving, sluggish, slow. Temperature is just a measurement of how energetically atoms are dancing on average. So when you touch something hot, what's really happening? The fast-dancing atoms in the hot object are bumping into the slower atoms in your hand. The fast atoms make the slow atoms speed up. Energy transfers from the hot thing to the cold thing through these atomic collisions. Your hand's atoms start dancing faster. You feel this as warmth spreading through your skin. Heat is kinetic energy, but it's kinetic energy at the microscopic level. It's the motion energy of countless tiny particles all moving and jiggling and bouncing. Zoom out and you can't see the motion, but zoom in, and there's a storm of movement. Think about an ice cube melting in your hand. The ice is cold, its atoms are moving slowly. Your hand is warm, its atoms are moving quickly. The fast atoms in your hand bump into the slow atoms in the ice. Energy flows. The ice's atoms speed up. When they speed up enough, they can't stay locked in the rigid structure of ice anymore. They start sliding past each other. The ice becomes water. You've used heat energy to break the bonds holding the ice together. This is why ice cubes always melt in warm water, never the other way around. The fast-moving water molecules bump into the slow-moving ice molecules. Energy always flows from fast movers to slow movers. Always. This is why heat flows from hot to cold. It's just energetic atoms sharing their motion with less energetic atoms nearby. Now think about a hot cup of coffee sitting on your table. Why does it cool down? The fast atoms in the hot coffee are bumping into slower atoms in the surrounding air. Each collision transfers a tiny bit of energy. Fast coffee atoms slow down a bit. Slow air atoms speed up a bit. Over and over, trillions upon trillions of times per second. The coffee gets colder. The air gets warmer. Eventually, they reach the same temperature, the same average atomic jiggling speed. We call this equilibrium. This is also why your ice cream melts on a hot day. The fast-moving atoms in the warm air bump into the slow-moving atoms in the frozen ice cream. Energy transfers. The ice cream atoms speed up. The structure breaks down. Solid becomes liquid. It's all heat energy, all atomic motion, all tiny invisible particles doing a frantic dance. Here's something wonderful to consider. When you feel cold, you're not feeling cold entering your body. You're feeling heat leaving your body. Your atoms are giving energy to the air. The atomic dance in your skin is slowing down. You interpret this as cold, but really it's the loss of heat. And when you stand in the sunshine and feel warmth, what's happening? Light from the sun is hitting you. That light carries energy. When light hits your skin, it makes your atoms jiggle faster. The atomic dance speeds up. You feel warmer. The sun, 93 million miles away, is making atoms in your skin dance faster. Think about that for a moment. Energy traveling across space, hitting you, becoming heat in your body. Heat is everywhere. It's in everything. Every object has atoms jiggling inside it. The hotter something is, the faster those atoms dance. Temperature is just the name we give to the average speed of that atomic dance. And heat energy is simply the total amount of jiggling motion in all those atoms combined. But atoms jiggling is only one way energy hides inside matter. There's another way, a deeper way. a way that stores enormous amounts of energy. And understanding this hidden energy will explain fire, food, batteries, and even how stars shine. Let's go even deeper. Inside every atom is a tiny nucleus at the center, packed with positive charge. And around that nucleus, negative electrons orbit like planets around a sun. Opposites attract. The positive nucleus pulls on the negative electrons. The electrons want to fall into the nucleus, but they also have motion that keeps them in orbit. It's a balance. Now, when atoms come near each other, their electron can rearrange. Sometimes an arrangement forms where the electrons are happier, more stable, lower in energy. When this happens, atoms stick together. We call this a chemical bond. And molecules are just atoms that have bonded together into stable arrangements. But here's what's crucial. Some molecular arrangements store energy, like a compressed spring waiting to release. Other arrangements are more relaxed, more stable, lower in energy. And when molecules transform from a high-energy arrangement to a low-energy arrangement, the difference has to go somewhere. That difference appears as heat, light, and motion. That's what we call a chemical reaction. Gasoline is a perfect example. Gasoline molecules are arrangements of carbon and hydrogen atoms. These arrangements are in a high-energy state. They're like springs, compressed and locked. The molecules desperately want to rearrange into something more stable, but they need a trigger. Fire is the trigger. Add a spark, a flame, just a little bit of heat to start things off, and the gasoline molecules break apart. They meet oxygen molecules from the air. And suddenly, everything rearranges. Carbon grabs oxygen to make carbon dioxide. Hydrogen grabs oxygen to make water vapor. These new arrangements are much more stable, much lower in energy than the original gasoline and oxygen. So where does the extra energy go? It explodes outward. The energy that was stored in the molecular arrangements comes pouring out as heat and light and expanding gases. That's combustion. That's fire. It's stored chemical energy becoming heat, light, and motion. Your body does the exact same thing, just more slowly and carefully. The food you eat, the sugar and fat and protein, these are all high-energy molecular arrangements. When your cells break down food molecules and combine them with oxygen from your breath, the arrangements transform into more stable forms. The extra energy is released. Some becomes heat, keeping your body warm. Some becomes the motion of your muscles. Some powers the chemical reactions in your brain that create thoughts. You are burning your food, just like an engine burns gasoline. You're just doing it slowly, carefully, in a controlled way. But the principle is identical. High-energy molecules becoming low-energy molecules, with the difference appearing as usable energy. Think about wood burning in a fireplace. The wood is made mostly of carbon. Those carbon atoms are arranged in complex molecules. When fire adds heat, the molecules break apart. Carbon meets oxygen from the air. They form carbon dioxide, a very stable, low-energy arrangement. The difference becomes warmth and light. A log is storing energy, energy from the sun that the tree captured years ago. The fire releases that stored energy all at once. Batteries work on this same principle. Inside a battery are chemicals arranged in high-energy states. When you connect the battery to a circuit, a chemical reaction begins. The chemicals rearrange into lower energy forms. The energy difference flows out as electricity. The battery isn't storing electricity exactly. It's storing chemical arrangements that can release energy when allowed to rearrange. Your muscles are similar. They store a special molecule that's like a compressed spring. When your brain signals a muscle to contract, this molecule releases its energy. The muscle fibers pull together. Chemical energy becomes motion. Then your body has to rebuild that spring molecule using energy from food. It's a constant cycle of storing and releasing and storing again. Here's the really profound part. Almost all chemical energy on Earth originally came from the sun. Plants use sunlight to build high-energy molecules from low-energy ingredients. They take carbon dioxide and water, both low energy, and use light energy to rearrange them into sugar and oxygen, which are higher energy. Plants are storing light energy in chemical bonds. When you eat plants, you're eating stored sunlight. When you eat animals that ate plants, you're eating stored sunlight one step removed. When you burn wood or coal or oil, you're releasing ancient sunlight that was captured by living things millions of years ago. Chemical energy is trapped light, trapped sunshine, trapped star power. And that brings us to the strangest form of energy. The form that flies through empty space. The form that has no mass, no substance, yet carries energy across the universe. The form that makes life on Earth possible. Think about standing outside on a sunny day. Close your eyes and face the sun. You can feel warmth on your face. But the sun is 93 million miles away. That's empty space between you and the sun. Nothing but vacuum. No air, no atoms, just emptiness. So how is energy getting from the sun to your face? What's carrying it across that vast nothing? The answer seems impossible. Light? But how can light carry energy? Light doesn't have mass. You can't hold light in your hand. It seems like nothing. Yet somehow this nothing is delivering energy to you from millions of miles away. Light is energy that travels. It's energy in pure form, energy without mass, energy as wave and particle simultaneously. Light is made of electromagnetic waves rippling through space itself. And these waves carry energy with them as they travel. Different colors of light carry different amounts of energy. Red light is low energy, orange a bit higher, yellow more, green even more. Blue carries quite a bit. Violet carries the most of the colors we can see. Beyond violet is ultraviolet, which we can't see, but we can feel because it carries enough energy to damage our skin. That's why ultraviolet light causes sunburns. It's high-energy light physically breaking molecular bonds in your skin cells. On the other end, beyond red, is infrared light. We can't see it either, but we can definitely feel it. Infrared is heat radiation. Hot objects glow with infrared light. When you feel warmth from a fire without touching it, you're feeling infrared light energy hitting your skin and becoming heat. X-rays are light too, just much higher energy than anything we can see. X-rays carry so much energy that they pass right through soft tissue in your body. Only dense bones and metals can stop them. That's why X-rays can photograph your skeleton. And beyond X-rays are gamma rays, the highest energy light in the universe, produced by the most violent events imaginable. On the low energy end, below infrared, are microwaves and radio waves. These are light too, just very low energy. Radio waves can pass right through walls. They don't have enough energy to damage molecules or heat things up much. But they're still light, still electromagnetic waves, still carrying energy through space. So light exists in this enormous spectrum. From ultra-low energy radio waves to ultra-high energy gamma rays, all of it is the same thing, just different amounts of energy. And all of it can travel across empty space forever, carrying energy along with it. Here's what makes light so special and strange. It doesn't need a medium. Sound needs air. Ocean waves need water. But light needs nothing. It travels through perfect vacuum happily. Light from distant galaxies has been traveling through space for billions of years, carrying energy the entire way, with nothing to travel through. It's energy in its purest traveling form. Now we come to something absolutely crucial for life on Earth. Plants can catch light. They have special molecules in their leaves that can absorb light energy. When a photon of light hits one of these molecules, the energy gets captured. The plant uses that captured light energy to build high-energy chemical bonds. It takes water and carbon dioxide and uses light to forge them into sugar molecules. This process, photosynthesis, is how plants eat. They eat light. They catch flying energy and trap it in chemical form. Those sugar molecules store the sun's energy in their molecular arrangements. And then, when anything eats the plant, they're getting that stored light energy. When the plant eventually dies and decomposes, that energy gets released. If the dead plant gets buried and compressed over millions of years, it becomes coal or oil, still storing ancient sunlight, waiting to be released as fire. Think about the journey. A nuclear reaction in the sun creates light. That light flies through space for 8 minutes. It hits a plant's leaf. The plant traps the light in a sugar molecule. A cow eats the plant. You eat the cow. Your body breaks down the molecules, releasing the energy. That energy powers your muscles as you move. The energy that's moving you right now started in the sun. You're running on starlight. And it's not just food. Nearly every form of energy we use ultimately comes from the sun. Solar panels, obviously, they directly convert light to electricity. But also fossil fuels, which are ancient captured sunlight. Wind power comes from wind, but what drives the wind? Temperature differences created by sunlight hitting different parts of Earth. Hydroelectric power comes from water flowing downhill. But what lifted the water up the mountain in the first place? Sunlight evaporated it from the ocean. The only major energy sources on Earth that don't come from the sun are nuclear power, geothermal energy from Earth's hot core, and tidal energy from the moon's gravity. Everything else traces back to light from the sun. Light is energy's messenger. It's how stars broadcast their energy across the cosmos. It's how energy travels without traveling through anything. It's pure energy, undiluted by matter, flying at the fastest speed possible through the fabric of space itself. We've now met energy's main disguises: motion, height, heat, chemical bonds, light, 5 forms, all different, all the same thing underneath. But the real magic happens when energy transforms, when it changes from one form to another, when it flows through the world, endlessly shape-shifting. That's what we explore next. Let's follow energy through a single, ordinary day. Your day. Because once you start looking for energy transformations, you see them everywhere. Every moment of your life is energy changing form, flowing, transforming, never stopping. You wake up in the morning. Before you even open your eyes, energy is at work. Your alarm rings. Inside that alarm, whether it's your phone or a clock, electrical energy is becoming sound energy. Electrons flowing through a speaker make it vibrate. Those vibrations push air molecules. The pushed air molecules become sound waves that travel to your ear. Sound waves make your eardrum vibrate. The vibrations become nerve signals. The nerve signals become the experience of hearing. All of this happens in a fraction of a second. Electrical to mechanical to pressure waves to mechanical to chemical to electrical to consciousness. Energy is shape-shifting faster than you can think. You get out of bed. Your muscles contract. Inside your muscle cells, chemical energy in molecules is breaking apart. Those molecules release their stored energy. Some becomes heat, warming your body. Some becomes the mechanical energy of your muscle fibers sliding past each other. Your leg lifts. Your foot touches the floor. Chemical became mechanical. You've just witnessed energy transformation. You go to the kitchen, you're hungry. Inside your body, your blood sugar is low. Your cells are running out of fuel. They need more chemical energy, and they're signaling desperately for it. You feel this as hunger, so you make breakfast. Maybe you cook eggs. You turn on the stove. If it's electric, electricity is flowing through a heating element. The moving electrons encounter resistance. That resistance converts their motion into heat. The heating element glows red. Electrical energy became heat and light. You place a pan on the stove. Heat flows from the burner into the pan through direct contact. The pan's atoms start jiggling faster. The pan gets hot. You crack an egg into the pan. The proteins in the egg white are complex folded molecules. Heat energy makes those molecules vibrate so violently that they unfold and tangle together. The clear egg white turns opaque. Chemical bonds are breaking and reforming. The egg is cooking. Heat energy is rearranging molecules. While the egg cooks, you make toast. Bread goes into the toaster. Electrical energy becomes heat in the toaster wires. The heat radiates toward the bread as infrared light. The light energy hits the bread and becomes heat again. The bread's surface gets hot. Sugars and proteins react with the heat. They turn brown and crispy. The Maillard reaction is taking place. Chemical energy is being released as flavors and aromas. Electrical became heat, became light, became heat, became chemical change. You eat your breakfast. Your teeth break the food into smaller pieces. Mechanical energy from your jaw muscles is breaking chemical bonds. The food goes down your throat. Your stomach churns it. Mechanical energy is mixing it with acid. The acid breaks more chemical bonds. The food moves to your intestines. Molecules get absorbed into your bloodstream. Your cells take in these molecules. Inside your cells, the most elegant energy transformation in nature begins. Your mitochondria, tiny power plants in every cell, take the food molecules and oxygen you've breathed in. They carefully break the molecules apart. The chemical energy stored in the food's molecular bonds is released. Some becomes heat, keeping your body at 98.6 degrees. Some get stored in new high-energy molecules that your cells can use later. This stored energy will power everything you do for the next few hours. You walk to your car. Every step is chemical energy, from breakfast becoming mechanical energy in your legs. You open the car door. Your arm muscles pull. Chemical becomes mechanical. You sit down. Your body compresses the seat. Kinetic energy from your falling body becomes potential energy in the compressed springs and foam. You start the car. You turn the key. Electrical energy from the battery flows to the starter motor. Electrical becomes mechanical. The motor turns the engine. In the engine's cylinders, gasoline mist meets air. A spark plug fires. Electrical energy creates a tiny lightning bolt. The lightning ignites the gasoline. Chemical energy stored in gasoline molecules explodes outward. The explosion pushes a piston. Chemical became heat, became mechanical. The piston turns a crankshaft. The crankshaft turns wheels. The car moves forward. Chemical energy in gasoline has become the kinetic energy of your moving car. But notice what else is happening. The engine is hot, very hot. In fact, most of the gasoline's energy is becoming heat, not motion. Only about a quarter of the energy moves the car. 3/4 becomes waste heat that radiates away. This is typical of energy transformations. Some energy goes where you want it. Much becomes heat. As you drive, friction between your tires and the road creates heat. Air resistance against your car creates heat. Your brakes get hot when you slow down. That's kinetic energy becoming heat. Your car's radio plays. Electrical energy becomes magnetic energy in the speakers, which becomes mechanical vibrations, which become sound waves. Your air conditioning runs. Electrical energy powers a compressor. The compressor does mechanical work. That work moves heat from inside your car to outside. You arrive at work, you turn off the car. But energy hasn't stopped transforming. Not for a second. The hot engine slowly cools. Heat energy flows from the metal into the surrounding air. Fast-moving atoms in the engine make slow-moving atoms in the air move faster. Hours later, the engine will reach the same temperature as the air around it. The energy has spread out completely. Inside at your desk, you turn on your computer. Electrical energy flows from the power outlet. Inside the computer, that electricity powers a processor. The processor does trillions of calculations per second. Each calculation requires energy. That energy becomes heat. Your computer has fans to blow the heat away, because if the heat builds up, it will damage the components. Electrical energy is becoming computational work and heat. You check your phone. Its screen lights up. Electrical energy from the battery becomes light through special crystals that glow when electricity passes through them. Your eyes receive that light. The light energy hits receptors in your retina. Those receptors convert light energy into chemical signals, then electrical nerve impulses. Those impulses travel to your brain. Somehow, mysteriously, those electrical patterns become your conscious experience of seeing your phone screen. Electrical became light, became chemical, became electrical, became consciousness. During your lunch break, you go outside. The sun is shining. Light energy that left the sun 8 minutes ago hits your skin. Your skin absorbs the light. The energy makes your skin's atoms vibrate faster. You feel warmth. Light became heat. Plants around you are absorbing sunlight too, using it to build high-energy molecules. Light is becoming chemical energy. You're watching it happen, though you can't see it directly. In the evening, you come home. You flip a light switch. Somewhere, maybe hundreds of miles away, coal is burning in a power plant, or water is falling through a dam, or uranium atoms are splitting in a reactor. That energy is converted to electricity. The electricity flows through wires to your house. It reaches the light bulb. In an LED bulb, electrons jump between different energy levels in a semiconductor. When they jump, they release light. Electrical energy became light. The room brightens. You cook dinner. More energy transformations. You charge your phone. Electrical energy flows into the battery. Chemical reactions reverse their normal direction, storing energy in high-energy molecular arrangements. Electrical is becoming chemical, getting stored for later. Before bed, you read. Your eyes absorb reflected light from the page. Light becomes chemical and electrical signals in your retina and brain. Your brain processes the signals. Energy is moving through neurons as electrical impulses and across synapses as chemical signals. You're thinking, and thinking is energy flowing in patterns through your brain. You feel tired. Your cells have used up much of the energy from breakfast and lunch and dinner. The high-energy molecules are depleted. Your body is telling you it needs rest so it can rebuild its energy stores. You lie down. Your body continues working through the night. Your heart beats, powered by chemical energy. Your lungs breathe. Your brain dreams. All of it is energy transforming constantly. This has been one day, one ordinary day, and every single moment involved countless energy transformations. Energy never stopped changing form, not once, not even for an instant. Your entire existence is energy flowing and transforming and dancing through different shapes. You are not a thing. You are a process. You are energy in motion. There's a pattern hidden in everything we've discussed. A deep pattern. A rule that governs all energy transformations. And once you see it, you'll understand why the universe behaves the way it does. Hot coffee always cools down. It never spontaneously gets hotter. A bouncing ball eventually stops bouncing. It never starts bouncing higher on its own. A broken glass never reassembles itself. Smoke never unscrambles itself back into a cigarette. These aren't just random observations. They're all examples of the same fundamental truth. Energy always spreads out. Always. It goes from concentrated to dispersed, from organized to disorganized, from useful to less useful. This is the arrow of time. This is why time flows forward. This is entropy, though we don't need to get caught up in technical terms. Let's understand this deeply. Imagine you drop a ball. The ball has potential energy at the top because of its height. As it falls, that organized potential energy becomes organized kinetic energy. The ball is moving as one unit, all its atoms traveling in the same direction together. Then the ball hits the ground. What happens to all that organized motion energy? Does it bounce back perfectly? No. Some becomes sound. The impact makes a noise. Sound is air molecules jiggling randomly in all directions. Some becomes heat in the ground. The atoms in the ground start jiggling a little faster from the impact. Some becomes heat in the ball itself. The ball deforms slightly on impact, and that deformation makes its atoms jiggle. Some does become upward motion, so the ball bounces, but not as high as it fell from. Do you see what happened? Organized energy, energy moving in one direction as a unit, became disorganized energy. Jiggling atoms, random sound waves, scattered heat. The total energy is still there, perfectly conserved, but it's spread out now. It's dispersed. And here's the crucial part. You cannot easily gather it back together. You cannot make all those randomly jiggling atoms spontaneously organize themselves to push the ball back up to its original height. It's not impossible in principle. The laws of physics don't forbid it. But it's so incredibly unlikely that it will never happen. Not in the lifetime of the universe. Not in 1 trillion lifetimes of the universe. Why? Because there are countless ways for energy to be disorganized and spread out, but only a few ways for it to be organized and concentrated. It's like dropping a box of marbles. They scatter everywhere. Organized arrangement became random scatter. Could all the marbles spontaneously roll back into the box in perfect order? The physics allows it, but the probability is so small it might as well be zero. This is why hot coffee cools. The heat energy in the coffee is relatively concentrated. It's in one small cup. The air around it is cooler. As fast jiggling coffee molecules bump into slow jiggling air molecules, the energy spreads. Some coffee molecules slow down. Some air molecules speed up. Energy is dispersing from a small concentrated region into a much larger region, going from organized to disorganized, from useful to less useful. Could all that heat spontaneously flow back into the coffee, making it hot again while the room gets colder? Physics allows it, but the probability is absurdly tiny. It won't happen. The universe doesn't work backward. This spreading, this dispersing, this disorganizing of energy is why things decay, why buildings crumble, why iron rusts, why your body ages, why nothing lasts forever. Organized structures require energy to maintain. Without constant energy input, everything naturally falls apart. Energy spreads, structure dissolves, order becomes disorder. But notice something important. You can create order. You can organize things. You clean your room. You build a house. You grow from a single cell into an adult human. How is this possible if energy always spreads out? The answer is crucial. You can create local order, local organization, but only by creating more disorder somewhere else. When you clean your room, you use energy from your body. That energy came from food. Making that food required sunlight and plant growth and countless energy transformations. All of those transformations spread energy out. The sun scattered enormous amounts of energy to grow the plants that you eventually ate, to get the energy to clean your room. You can push back against disorder locally, but the price is always more disorder globally. The universe as a whole always moves toward more spread out, more disorganized energy. You're like a tiny eddy in a river, swirling in a circle while the river flows past you. You can maintain your local organization, but only because you're part of a much larger flow toward disorder. This is why living things need constant energy input. You need to eat every day. Plants need sunlight every day. If the energy stops flowing, you can't maintain your organized structure. You decay. Life is a constant battle against energy dispersal. You're not fighting to stay the same. You're running up a down escalator. You have to keep running just to stay in place. This is also why we need power plants and engines and batteries. Nature constantly spreads energy into useless heat. We need machines to reconcentrate it, to gather it back into useful forms. But those machines always create more waste heat than the useful energy they produce. They have to. It's not a flaw in the design. It's a fundamental law of nature. The universe is winding down. Energy is spreading out. Billions of years from now, all the energy in the universe will be perfectly evenly distributed. Every point in space will have the same temperature. Nothing will be able to happen anymore because nothing can happen without energy flowing from one place to another. Scientists call this heat death. It's the ultimate fate of everything. But that's unimaginably far in the future. For now, for billions of years to come, there's still enough concentrated energy to power stars and life and thinking beings like you. The story isn't over, but the ending is already written. Energy will spread until there's nowhere left to spread to. Now let's talk about something practical. Something engineers and scientists have been wrestling with since the Industrial Revolution. If energy is conserved, if it can't be destroyed, why do we constantly run out of it? Why do we need to keep burning fuel, keep generating electricity, keep eating food? If energy never vanishes, shouldn't we be able to use the same energy over and over? The answer is in what we just discussed. Energy doesn't disappear, but it becomes less useful. It spreads out into forms we can't easily use. This is the efficiency problem. Think about a car engine. You put gasoline in the tank. That gasoline stores chemical energy. When the engine burns the gasoline, all that energy gets released. But here's the shocking truth. Only about 25% of that energy actually moves your car. Only a quarter. Where does the other 75% go? Heat. It becomes heat. The engine gets hot. The exhaust pipe gets hot. The radiator releases heat into the air. All of that is energy from your gasoline. Energy that cost you money. Energy that could have moved your car. But instead, it's heating up the atmosphere around your car, doing nothing useful. This isn't because car engines are badly designed. Modern car engines are marvels of engineering. The problem is more fundamental. Burning fuel creates heat. Heat is random molecular motion, and it's very hard to convert random motion into organized motion. You can do it partially, but never completely. Most of the heat just escapes. The same thing happens with coal power plants. They burn coal to boil water. The steam turns turbines. The turbines generate electricity. But the overall efficiency? Only about 35%. 65% of the energy in the coal becomes waste heat that goes up cooling towers or into nearby rivers. 2/3 of the coal's energy is wasted, not because of bad engineering, but because the laws of physics make perfect efficiency impossible. Old-fashioned incandescent light bulbs are even worse. You know how they get hot? That's wasted energy. An incandescent bulb converts only about 5% of the electricity into visible light. The other 95% becomes heat. You're running a tiny heater that happens to produce a bit of light as a side effect. LED bulbs are much better. They convert about 50% of electricity into light. That's 10 times better than incandescent bulbs. But even they can't reach 100%. Some energy always leaks away as heat. Your own body faces the same limitation. You eat food. Your cells extract the chemical energy. But your body is only about 25% efficient at converting food energy into useful work. If you lift a weight, only a quarter of the energy from your last meal actually lifts the weight. The other 3/4 becomes heat, keeping your body warm. Actually, that's not waste in the usual sense. Your body needs to stay warm. So the waste heat is actually serving a purpose. But if you're trying to do mechanical work, most of the food energy doesn't contribute to that work. It just keeps you alive and warm. This inefficiency is built into the universe. It's not something we can engineer away. The second law of thermodynamics, as physicists call it, guarantees that every energy transformation will produce some unusable waste heat. You can minimize it. You can improve efficiency. But you can never reach perfection. Here's why this matters for our civilization. We're burning through fossil fuels at an enormous rate. Coal, oil, natural gas. These fuels took millions of years to form. They're concentrated energy from ancient sunlight. And we're burning them mostly to create heat that escapes into the atmosphere. Most of the energy doesn't do the work we want. It just makes the planet warmer. If we could build perfectly efficient machines, we'd need much less fuel. But we can't. Physics won't allow it. So we need to find energy sources that are renewable. Solar panels collect energy from the sun. Even if they're only 20% efficient, the sun keeps shining. Wind turbines catch moving air. Even if they're only 40% efficient at best, the wind keeps blowing. The sun's energy is spreading out anyway. We might as well catch some before it disperses completely. But here's something beautiful in all of this. Even though no transformation is perfect, even though energy always leaks into unusable forms. The universe keeps perfect accounts. Every single joule, every unit of energy is tracked. Nothing is ever truly lost. It just becomes less concentrated, less organized, less able to do work. Engineers dream of beating this, of finding a way to recapture all the waste heat and reuse it. But it's like trying to unscramble an egg. Once energy spreads into random heat, gathering it back requires more energy than you get out. You can't win. You can't break even. You can only try to minimize your losses. This is both humbling and freeing. Humbling because it reminds us we're working within constraints we didn't choose and can't change. Freeing because it helps us focus on what actually matters. We can't create energy or destroy it. We can only borrow it briefly, use it once, and return it to the universe in a more dispersed form. We're not owners of energy. We're temporary users, brief editors of its form. And yet, in that brief moment when energy passes through you, when it flows through your body and brain, it creates something remarkable. It creates consciousness, it creates thought, it creates life. Most of the energy becomes forgettable waste heat, but a tiny fraction becomes you. And that makes all the difference. We've talked about energy as something separate from matter. Energy is what matter has or does. A ball has kinetic energy. Your body has chemical energy. But the ball and your body are made of matter, which is different from energy, right? This seemed obvious for centuries. Matter is stuff. Atoms, molecules, solid things you can touch. Energy is the ability to make things happen. Two different categories, two different concepts, matter and energy. Then, in 1905, a young patent clerk in Switzerland published a paper that shattered this distinction forever. His name was Albert Einstein. And his idea was so radical, so impossible sounding, that even he wasn't sure people would believe it. Einstein proposed that matter and energy are the same thing. Not similar, not related, the exact same thing. Matter is concentrated energy. Energy is dispersed matter. They're two forms of one substance. You can convert matter into energy. You can convert energy into matter. The universe doesn't have matter and energy. It just has mass energy, one thing expressing itself in two ways. The equation that expresses this is probably the most famous equation in history. E equals mc squared. Energy equals mass times the speed of light squared. Let's understand what this means. The E is energy. The m is mass, the amount of matter in an object. And the c is the speed of light. Light travels at about 186,000 miles per second. That's already an enormous number. But the equation says you square it. You multiply it by itself. 186,000 times 186,000. So even a tiny amount of mass, when multiplied by this huge number squared, equals an enormous amount of energy. A paperclip has about 1 gram of mass. According to Einstein's equation, that paperclip, if you could convert all its mass to energy, contains enough energy to power a large city for weeks. 1 gram equals about 20,000 tons of TNT. That's the explosive power of the bomb that destroyed Hiroshima, all hiding in a paperclip. This sounds insane. How can matter contain that much energy? Where is it stored? The answer is profound. It's not stored anywhere. Matter is energy. The mass of an object is energy that's been given form. When you hold a rock, you're holding solidified energy, frozen energy, energy that has taken shape and structure but is fundamentally still just energy. For most of human history, this conversion between matter and energy never happened, at least not in ways we could detect. Chemical reactions, burning, digestion, all of these involve energy transformation. But they don't convert matter to energy. The atoms stay atoms. The mass stays mass. Only the arrangements change. But in the 20th century, we learned to split atoms. Nuclear fission. When a uranium atom splits, something remarkable happens. The pieces weigh slightly less than the original atom. Not much less, just a tiny fraction of a percent. But that missing mass has to go somewhere. Where does it go? It becomes energy, pure energy. Heat, light, radiation, motion. The missing mass converted completely into energy according to Einstein's equation. That tiny bit of missing mass, when multiplied by c², equals enormous energy. That's what powers nuclear reactors. That's what made atomic bombs so devastating. Matter becoming energy. The sun does this constantly. Every second, the sun converts about 4 million tons of matter into energy. 4 million tons just disappears, transformed completely into light and heat that radiate into space. The sun is burning matter itself. It's 4 million tons lighter every second. And it's been doing this for 5 billion years. That's how much mass the sun contains, and that's how powerful Einstein's equation is. This revelation changes everything about how we understand the universe. You're not just a collection of atoms. You're an amount of energy that has taken biological form. Your mass, the weight you feel when you stand on a scale, that's measuring your energy content. You are frozen starlight. You are shaped energy. You are E equals mc², walking around. This also means the universe's energy content includes all its matter. When we talk about energy conservation, we have to include matter. Matter can become energy. Energy can become matter. The total of both, the total mass energy, is what's conserved. And that total has remained exactly the same since the beginning of the universe. Nothing has been added. Nothing has been removed. The universe has been rearranging the same total amount of mass energy for nearly 14 billion years. But this raises a profound question. A question that leads us to the ultimate mystery. Here we are, finally, at the deepest question. We know energy is conserved. It can't be created or destroyed. The amount in the universe is fixed. But fixed at what? What's the total? And more importantly, where did it come from originally? Think about the Big Bang. 13.8 billion years ago, the entire universe was smaller than an atom. Then it exploded outward. Space expanded. Matter formed. Energy spread out. The universe has been growing and cooling ever since. But here's the question. Where did all that initial energy come from? What caused the Big Bang? What provided the initial energy that became everything? One possibility is that the universe always had this energy. It's eternal. It never began. It was always here, just in different forms. But that's not really an answer, is it? It's just pushing the mystery back. Okay, the energy is eternal, but why? Why does energy exist at all? Another possibility is even stranger. Maybe the universe's total energy is zero. How is that possible? You look around and see stars, galaxies, planets, people. Clearly, there's energy everywhere. How could the total be zero? The answer has to do with gravity. Gravity is a force, but it's also related to energy. And gravity's energy is negative. Imagine pulling two objects apart against gravity's pull. You have to add energy to do this. That means bringing them together releases energy. The energy of objects pulled together by gravity is lower than the energy of objects far apart. So gravity contributes negative energy. Now think about the universe. All the matter, all the stars, all the galaxies, they're all pulling on each other through gravity. That gravitational pull represents an enormous amount of negative energy. Could it be that the negative energy from gravity exactly cancels the positive energy from matter, light, heat, and motion? Could the universe's total energy actually be zero? If so, the Big Bang wasn't creating energy from nothing. It was creating equal amounts of positive and negative energy from nothing. Zero became plus 10 and minus 10. The books still balance at zero. The universe could be the ultimate free lunch. A free lunch where the meal and the bill arrive together and they exactly cancel out. This is speculation, of course. We don't know for sure. Measuring the total energy of the universe is extraordinarily difficult. We can't step outside the universe and weigh it. We're inside, trying to measure the whole from within. It's like a fish trying to measure all the water in the ocean while swimming in it. Some scientists believe the total is zero. Others think the total is positive. A few think it might even be infinite, that the universe goes on forever in space and contains infinite energy. We simply don't know. And there's something else we don't know, something even more mysterious, something discovered only recently, something that makes up most of the universe's energy, and we have no idea what it is. In the 1990s, astronomers made a shocking discovery. They were studying distant supernovas, exploding stars that are so bright they can be seen across billions of light years. By studying these supernovas, they hope to measure how the universe's expansion is slowing down. You see, we've known since the 1920s that the universe is expanding. Galaxies are moving apart from each other. Space itself is growing. But gravity should be slowing this expansion down. All the matter in the universe is pulling on all the other matter. This pulling should gradually slow the expansion, like friction slowing a spinning top. So astronomers were trying to measure how much the expansion has slowed over billions of years. They expected to find that distant galaxies, which we see as they were billions of years ago, were moving apart faster than nearby galaxies, which we see as they are more recently. Instead, they found the opposite. The universe's expansion is speeding up. Distant galaxies are moving apart slower than nearby ones. The expansion was slower in the past and faster now. Something is pushing the universe apart. Something is making the expansion accelerate. This shouldn't be possible. Nothing in our understanding of physics predicted this. Gravity pulls things together. It doesn't push them apart. What could be pushing all of space apart, overcoming gravity, making the expansion faster and faster? We have no idea. None. We've given it a name. We call it dark energy. But that's just a label for our ignorance. Dark energy is something that fills all of space. It doesn't clump like matter. It spreads smoothly everywhere. And it has a strange property. As space expands, dark energy doesn't dilute. Its density stays constant. So, as the universe gets bigger, there's more total dark energy. And here's the staggering part. We've measured how much dark energy there is. It makes up about 68% of all the energy in the universe. 68%. More than 2/3 of everything is dark energy. Regular matter, the stuff that makes stars and planets and you, makes up only about 5%. The rest, about 27%, is dark matter, another mystery we don't fully understand. So we've spent this entire documentary talking about energy. We've learned about kinetic energy, potential energy, heat, chemical bonds, light, nuclear energy. We've learned how energy transforms, how it's conserved, how it shapes everything that happens. And now I have to tell you that everything we've discussed is only 5% of the total energy in the universe. The other 95%? We don't know what it is. We can measure its effects. We can see what it does. Dark energy pushes space apart. Dark matter holds galaxies together. But what are they really? What's their nature? We have no idea. This is humbling. We've learned so much about energy. We've unlocked its secrets. We've built entire civilizations on our understanding of how energy works. We can split atoms. We can capture sunlight. We can convert mass to energy. We understand the principles. We know the laws. And yet most of the universe's energy is completely mysterious to us. We're like people who have learned everything about the 5% of an iceberg above water, while being completely unaware that 95% is hidden beneath. This doesn't mean our understanding is wrong. The energy principles we've learned are real and true and useful. They govern the 5% we can interact with. They explain everything in our daily lives. But they're incomplete. There are deeper mysteries waiting to be solved. Scientists today are searching for answers. They're building experiments, making observations, developing theories. Maybe you, someone watching this right now, will be the one who figures it out. Maybe you'll be the person who explains dark energy, who reveals what makes up most of the universe. The mystery is still open. The adventure continues. And in a way, this is perfect, because energy has always been mysterious. Our ancestors felt its effects without understanding it. For thousands of years, fire and motion and life were pure mystery. Then science began uncovering the truth. We learned about conservation. We learned about transformation. We learned that energy and matter are the same. Each answer revealed new questions. Each solution opened new mysteries. We're much further along that path now, but the path hasn't ended. It never ends. Each generation pushes a little farther into the unknown, and the unknown is still enormous, still waiting, still full of wonders we can barely imagine. Let's return from these cosmic mysteries to something more personal, more immediate. Let's return to you. Right now, as you watch this or read this, energy is flowing through you. Your heart is beating. That's chemical energy becoming mechanical motion. About once per second, all day, all night, your entire life. Your heart has probably beaten 3 billion times so far. 3 billion energy transformations from chemical to mechanical. Your lungs are breathing. Air flows in, carrying oxygen. Air flows out, carrying carbon dioxide. Each breath involves dozens of muscles contracting and relaxing. Chemical energy powers every breath. You take about 20,000 breaths per day. 20,000 cycles of energy transformation. Your body is warm. Your core temperature is about 98.6 degrees. That warmth is energy. Heat energy from countless chemical reactions. Your cells are burning fuel continuously, keeping you warm. If they stopped, you'd cool to room temperature within hours. You're a small fire, carefully contained, constantly fed, never going out as long as you live. Your brain is active right now. Neurons are firing. Electrical impulses are racing along nerve fibers. Chemical signals are crossing synapses. Every thought, every memory, every sensation is energy flowing in patterns through your brain. About 20% of your body's total energy goes to your brain. Your brain is only 2% of your body weight, but it uses 1/5 of your energy. Thinking is expensive in energy terms. Your eyes are open. Light is hitting your retinas right now. Photons, particles of light energy, are being absorbed by special molecules in your eye. Those molecules change shape when they absorb light. That shape change triggers a cascade of chemical reactions. The chemical reactions create electrical signals. The signals travel to your brain. And somehow, mysteriously, you see, light became chemistry, became electricity, became vision, became conscious experience. Energy transformed into awareness. You are not a static thing. You're not an object sitting still. You're a process, a continuous flow, a river of energy that has taken a temporary form. The atoms in your body are constantly being replaced. The food you eat becomes you. The old you becomes waste and heat. The atoms that were you last year are mostly gone now, but you remain. The pattern remains, the energy flow remains. Think about this. You started as a single cell, one tiny fertilized egg. That cell had information in its DNA, instructions for building you. But information doesn't build things. Energy builds things. That single cell used energy to divide into 2 cells, then 4, then 8. Each division required energy. As you grew, energy from your mother's food flowed into you. That energy built your body. It assembled proteins. It grew your organs. It wired your brain. You were built by energy. You are maintained by energy. You will eventually be dismantled by energy processes. Birth, life, and death are all energy transformations. You are energy that learned to preserve itself. Energy that learned to repair itself. Energy that learned to reproduce itself. You are energy that became alive. And more remarkably, you are energy that became aware. Somewhere in the flow of energy through your brain, consciousness emerges. The ability to know that you exist. The ability to think about thinking. The ability to understand energy itself. You are energy that woke up and looked at itself. This raises a profound philosophical question. What are you, really? Are you the atoms that make up your body? But those atoms are constantly replaced. Are you the pattern those atoms form? But that pattern slowly changes as you age. Are you your consciousness? But consciousness emerges from energy flowing through matter. Perhaps you are none of these separately. Perhaps you are the flow itself. You are the process. You are energy in a particular shape, flowing in a particular pattern for a particular period of time. You are not a noun. You are a verb. You are not a being. You are a becoming. You are not a thing. You are a happening. And when you die, the energy doesn't disappear. It can't. Energy is conserved. The energy that animated you will disperse. Some will become heat. Some will be used by bacteria and fungi as they decompose your body. Some will return to the earth. Some will be taken up by plants. The atoms will scatter. The pattern will dissolve. But the energy persists. It cannot do otherwise. In a very real sense, you are immortal. Not you as a pattern, not you as a consciousness, but you as energy. The energy that makes you is eternal. It existed before you were born, borrowed from the universe and temporarily shaped into your form. When you die, that energy returns to the pool. It will become other things, other patterns, maybe other living things. The energy that thinks your thoughts right now will someday be thinking someone else's thoughts, or lighting a star, or warming a planet, or flowing through empty space as light. You are a temporary eddy in an eternal river, a brief pattern in an endless flow. You are the universe experiencing itself. You are energy looking at energy. You are a way for the cosmos to know itself. So we return to our original question. What exactly is energy? After 2.5 hours of exploration, after following energy through fire and food and stars and galaxies, after meeting it in all its forms and watching it transform, we can finally give an answer. Energy is not a thing. It's not a substance you can hold or touch. It's not made of anything. Energy is a property, a measurement, an accounting system the universe uses to keep track of what's happening. Energy is the ability to make things happen. It's the capacity to cause change. It's the potential for events to occur. When something happens, anything happens, energy is flowing and transforming. Energy is the answer to the question, why do things change? But it's more than just an abstract concept. Energy is real. You can measure it. You can calculate it. You can predict with perfect accuracy how much energy a system has and where that energy will go. Energy is nature's currency. It's spent here and earned there. It's traded and transformed and moved around. But the total in the universe's account never changes. Never. The books always balance perfectly. Every event in the history of the universe, from the Big Bang to this present moment, has been energy redistributing itself, changing forms, moving from place to place, spreading out. The Big Bang was energy exploding outward. Stars are energy fusing and radiating. Planets are energy spinning and moving. Life is energy organizing itself into complex patterns. Thinking is energy swirling through brains. Everything is energy dancing. The conservation law tells us something profound about reality. The universe is a closed system. Nothing comes in from outside. Nothing leaves to the outside. Everything that happens is just internal rearrangement. The universe is playing with a fixed set of pieces. Those pieces are units of energy, and every event is those pieces moving around the board. Time itself is tied to energy redistribution. Time flows forward because energy spreads out. If energy didn't spread, if it stayed concentrated forever, time wouldn't have a direction. The past would be indistinguishable from the future. But energy does spread. It always spreads. And that spreading is time passing. Time is energy's journey from concentrated to dispersed. Understanding energy has practical importance. It's the foundation of all technology. Every machine we've ever built is a device for transforming energy from one form to another. Engines transform chemical energy to motion. Generators transform motion to electricity. Light bulbs transform electricity to light. Computers transform electricity to information processing and heat. Understanding how these transformations work lets us build civilization. We can predict how much energy we need for any task. We can calculate efficiency. We can compare different energy sources. We can solve problems by tracking where energy goes. Every problem in physics ultimately comes down to following the energy. Where is it? What form is it in? Where's it going? Answer these questions and you understand what's happening. But understanding energy also reveals profound truths about existence itself. The conservation law means the universe is in some sense eternal. The total energy has always been here and always will be. It can't increase, it can't decrease, it can only rearrange. The universe is fundamentally unchanging in its totality, even as it constantly changes in its details. You are a temporary pattern in this eternal substance. Your consciousness is energy swirling in an extraordinarily complex pattern inside your skull. When that pattern dissolves, the energy remains, ready to form new patterns. You were energy before you were born, shaped into your current form. You will be energy after you die, dispersed into new forms. Birth and death are not beginnings and endings. They're transformations. They're energy changing shape. This perspective can be comforting. Nothing is truly lost. Everything continues in a different form. The people you love who have passed away, their energy persists. The atoms that were them are now part of trees, air, earth, other living things. The energy that powered their thoughts and warmed their bodies has spread out, but it's still here, still part of the universe, still obeying the same eternal laws. Or this perspective can be unsettling. If you're just a temporary pattern, just energy swirling for a brief moment, what makes you you? What gives life meaning if you're just physics happening? These are deep questions. Questions that science alone cannot fully answer. Science can tell you what you are. What you mean is something you must decide for yourself. But perhaps there's beauty in being a pattern that knows it's a pattern. Perhaps there's wonder in being energy that became aware of itself. Perhaps meaning isn't something you have. Perhaps meaning is something you are. In every moment of consciousness, in every act of love, in every creative thought, energy is doing something remarkable. It's organizing itself. It's fighting against the universal tendency toward disorder. For a brief, glorious moment, energy is building instead of dispersing, creating instead of destroying, living instead of dying. Think back to our opening images, the child on the swing, rising and falling. Now you see it differently. Potential energy becoming kinetic and back again. The gravitational field storing and releasing energy with each arc. The lightning splitting the sky. Electrical potential energy suddenly releasing, creating heat and light and sound. Millions of volts finding a path to ground, transforming in an instant. The waterfall crashing down. Gravitational potential energy at the top becoming kinetic energy in the falling water, becoming sound and spray and heat at the bottom. Your heart beating. Chemical energy in ATP molecules becoming the mechanical energy of muscle contraction. 3 billion transformations in your life so far. Billions more to come. The campfire crackling, chemical potential energy stored in wood by ancient sunlight, released all at once as heat and light. The logs returning their borrowed energy to the universe. The flower opening. Energy from today's sunlight being captured, being transformed into the chemical bonds that let petals unfold. Life organizing energy into beauty. Every one of these moments is energy at work, energy changing form, energy flowing through the universe, energy being conserved perfectly while creating everything we see. Energy is the answer to why things happen. It's the reason for motion, it's the cause of light, it's the source of warmth, it's the power behind life, it's the currency of thought, it's the flow of time. Energy is what makes reality real. Without energy, nothing would happen. Ever. The universe would be frozen, static, dead, a snapshot with no progression. But energy does exist. It flows, it transforms, it dances through countless forms. And because of that, the universe is alive with change, with motion, with events, with happenings, with existence itself. You began this film with energy from your breakfast. Chemical bonds in food became the electrical impulses in your brain that let you understand these words. You'll leave with energy in your mind. Ideas and connections and insights are patterns of energy stored in the neural pathways of your brain. Knowledge is organized energy. The energy that makes you think these thoughts right now, the energy that creates your consciousness at this exact moment, is the same energy that lights the stars, that moved through ancient seas, that powered dinosaurs, that will someday power beings we cannot imagine. It's all the same energy, eternally recycled, eternally conserved, eternally in motion. Everything is energy. The ground beneath your feet, the air in your lungs, the light reaching your eyes, the warmth on your skin, the thoughts in your mind, the consciousness reading or hearing these words. All of it, every bit of it, is energy expressing itself in different forms. You are energy, not in a metaphorical sense, not as poetry. Literally, physically, measurably, you are energy given form. You are a standing wave in the energy field of the universe, a persistent pattern, a shape that energy has taken for a while. And now you know. You understand what has puzzled humans for thousands of years. You see the invisible force that powers everything. You know the answer to one of existence's deepest questions. What exactly is energy? Energy is everything, and everything is energy, including you, especially you. The image fades slowly to black. But energy doesn't fade. It never can. It transforms into something new, always, forever, without end.